Good morning everybody. So today we will resume our discussion on fresh concrete properties. We were talking yesterday about how we can modify existing methods to actually try and determine some specific properties of flowable concretes like self-compacting concrete. We first talked about the slump-based test, how we can actually modify the regular slump test for a flowable concrete or a very highly workable concrete and obtain some interesting data primarily in terms of how fast the slump actually occurs apart from the total slump that is also measured in the same test. So, in one test you are now able to get two parameters instead of just one. Okay. So, that seems to match the requirements for rheology quite well. And again for the self-compacting concrete you have the slump flow test where we are looking at the overall spread of the slump cone as well as the time to spread 500 millimeters. So, both these give us an idea about the rheological properties of the concrete. The other tests which are very specific to self-compacting concrete involve the flow through obstacles, primarily because self-compacting concrete is not vibrated, it has to flow between reinforcement bars and try to completely encapsulate the inside of the formwork which it is required to fill. So, for that what you need to ensure is the aggregate size and the aggregate content are controlled in such a fashion that the SCC can easily flow between the reinforcing bars. So, one of the tests that is prevalent for this kind of a determination is the U-tube test. U-tube these days is YOU tube, but this is just the U tube because the tube is shaped like a U and there is one limb of the tube where the concrete is first filled and there is a gate here and that gate basically has an obstacle right behind it. Okay. So, you fill up the concrete at one end while the gate is closed. When you open the gate, the concrete has to flow through the obstacle to the other side. Of course, if you imagine that you pour water instead of concrete, it will flow until it equalizes on both sides. There will be no difference in heights on both sides. But with concrete, because of its nature, because of its lack of flowability in some instances or because the aggregates start getting blocked at the obstacles, you may not have the entire concrete rising in the second limb. Okay. So, for self-compactability, what you need to ensure is the difference in the height is less than 3 centimeters. Okay. In both limbs of the U-tube, the difference in the height should be less than 3 centimeters. So, once you have a concrete that satisfies that requirement, it is also called self-compactable because one of the important characteristics that it needs to satisfy is the passing ability to pass between reinforcement. Okay. Of course, the V funnel test is more related to the flowability again. Now, here you pour the concrete into this V-shaped funnel, the gate or trap door at the bottom is first closed. Okay. After the concrete is completely filled, you open the trap door and then allow the concrete to fall through the funnel. So, again if you imagine if it is water, it is going to fall almost immediately, it is going to come out in a single stream. Okay. If you imagine it is going to be a very cohesive or very stiff concrete, it will not fall at all, right, it will not fall out of this opening at all. If it is semi-stiff concrete, it may fall out but start coming down in chunks, it will not really come down as a single pour. For self-compactability, you want it to come down typically as a single pour. And generally what there are specifications about is the time it takes for the entire concrete to get emptied from a V funnel. You can also do this test in different way. You can let the concrete stay inside for 5 minutes, right. What will that do? If there is any segregation, it will happen in those 5 minutes, right. And then you allow the concrete to fall out of the trap door. So, if the concrete starts segregating, it does not have a uniform flow out of the V funnel, right. If it is uniform still after the end of 5 minutes, it has a consistent behavior, then it will come out as a single pour rather than coming out in chunks. Okay. So, that is an important test V funnel. There is another test which is called Orimet. Again this involves the flow of self-compacting concrete through an orifice which is opened and you allow the concrete to flow out, measure the time taken for the flow and that is related to the flowability of the concrete. So, generally 6 to 12 seconds is recommended as far as the V funnel test is concerned. Okay. All these guidelines for testing as well as the conditions for acceptance of the SCC are given in a standard or in a draft guideline which is called EFNARC. EFNARC is a European organization which is consisting of experts from the industry and academia and they had a big project on self-compacting concrete in the early 2000s and based on that they came out with EFNARC guidelines for SCC. And these are again available on the internet. And these guidelines can be utilized for actually designing the SCC, understanding the characteristics of the SCC, testing it understanding what changes you need to make in the mix in case it is not working properly, all that is very clearly given in this guideline. So, while SCC may not be there in most of your standards, it is definitely there in the guidelines. The test methods for SCC like the YouTube, vFunnel, slump flow, all these have now found a position in the standards also. Not in Indian standards yet, but they are going to be introduced in the Indian standards also in the fresh concrete testing standards, right. In American standards, you already have standards which pertain to these tests. So, test methods are made into the standards. The design of the concrete is not yet standardized, or there is no guideline published by the standards organization or concrete institutes in different countries for the design of these special types of concretes. So, for design, the best strategy is to still use the guidelines for SCC which are given by EFNARC. I think the last version came out in 2005. Beyond that, there is no real change in the methodology of design of SCC. But what I will show you is towards the end of this chapter, we will talk about a specific method for mixed design which does a little bit better than just take up guidelines from a well publicized document. So, what we have tried to do in this case, it was related to the PhD thesis of one of the students, and he has worked on a specific methodology that combines the particle packing approach along with rheology to understand how well we can describe the properties of SCC and control it through a proper mixed design. So, I will talk about that at the end of this chapter. There is another test which determines the passing ability, that is called the L box test. Again, this box is shaped like an L, right, and the vertical limb of the box is where you fill up the concrete. Again, there is a gate here. Beyond the gate, there is an obstacle which consists of reinforcement. So, once you open the gate, the concrete starts flowing through the obstacle. Okay. For the concrete that is highly flowable and has aggregate size which is well controlled and aggregate content that is less enough, it will easily flow through the obstacle and reach the other end. And once it reaches the other end, a highly self-compactable concrete will have a ratio of heights at both ends which is close to 1. Generally, a ratio between 0.8 and 1 is recommended for self-compactability. For concrete that has too much coarse aggregate or that has improperly sized coarse aggregate, what will happen is it will start getting blocked at the obstacle and not be able to cross that barrier, and because of that the height differences will be very high. There are some concretes that are so cohesive that they may stop flowing, right, they may not even flow to the other end. So, again this is a test which is probably the most stringent test amongst all SCC tests. The most stringent one is the L box test. So, if a concrete passes the L box test, you can consider that it will pass most of the other tests. What I have not covered here is something called the J ring test. Okay. So, when you have a slump flow test, what you do is this is your slump cone, you have a ring on the outside. Okay, I am just drawing the plan. So, this is the ring on the outside. So, in elevation, if you look at the slump cone, you have a ring on the outside, and this ring is basically consisting of reinforcement bars. Okay. So, once you lift up the slump cone, the concrete has to flow, but now instead of flowing freely, it will have to flow between the reinforcement bars. And for the J ring test, the slump flow that you get, flow should be not less than 50 millimeters less than the regular slump flow. So, if you are doing without the J ring, if you get a certain value, you repeat the test with the J ring, the slump flow should not be more than 50 millimeters different for a good self-compactable concrete. That means, in one test you are not only measuring the flowability, you are also measuring the passing ability. So, the J ring, U-tube and the L box, these are tests for passing ability. For flowability, again you have slump flow, vFunnel test. Okay. Both of these are testing the flowability of the concrete. Now, in general, what I was talking about earlier is that the presence of obstacles could cause blocking if you do not design your concrete properly, if you have too much coarse aggregate or if you have too large sized coarse aggregate. Okay. And then of course, you can also evaluate resistance to segregation. The simplest way to do that, of course, we already saw that you can do that in a vFunnel test also by letting the concrete sit inside the funnel for some time and then opening the trapdoor. The other strategy is to simply put the concrete in a bucket, allow it to settle for about 15 minutes, then pour out the top half of the bucket. What will that do? If the concrete is segregated, the top half that gets poured out will only be paste or mortar, right. So, then you can evaluate the amount of coarse aggregate that you have in the top half and get an estimate of how much segregation has actually occurred. Very simple, easy to do, right. It is not a big deal at all. But of course, you can also evaluate after concrete has hardened, you can take a core and see how the aggregates are distributed. If you have a uniform distribution of the aggregates all across the cross section, it is a good mix, but of course by then it is too late because the concrete is already hard, right. The other way to check the uniformity of concrete that has been laid is to just do an ultrasonic pulse velocity test. If you have a column of concrete that has been laid with self compacting concrete, if you are worried that segregation may have happened leading to an increase in the coarse aggregate fractions at the bottom, when you take the pulse velocity, the relative differences in the quality can easily be brought out with the help of the pulse velocity test. Okay. So, having looked at the characteristics of self compacting concrete and how we can evaluate those, let us now look at a strategy that was worked out based on a PhD thesis of Dr. Prakash, who worked here, passed out in 2009, now he is an assistant professor at IIT Bombay. So, he has devised this methodology for design of self compacting concrete combining particle packing and rheology. So, let us look at how this is done. So, this is a stepwise process. First is the optimization of the powder combination or composition, that means the degree of fly ash replacement of cement. So, again we have assumed here that most SCCs will have fly ash as the cement replacement material, because that is what works in most cases to improve the flowability without really causing an excess increase in the binder content. Okay. If you have to use slag or silica fume, you may get mixes that are difficult to control. With fly ash it is much easier, typically, I am not saying all the time, but typically it is much easier with fly ash. The optimization of the aggregate combination is done next with a particle packing approach. Of course, if you look at the methodology of the powder composition optimization, you will see that that is also essentially based on particle packing, but both these are different empirical techniques. We are not again following the same EMA software here, although you can do the same to some extent with the EMA software also. Okay. The next is optimization of aggregate combination, and finally once the aggregate combination is optimized, you know exactly how much volume of paste you require to enter the voids left behind by the aggregates, and on top of that what is the excess paste that you require to make the concrete flowable. So, that is what is the determination of paste content required for the specific slump flow applications. Okay. And then of course, you need to realize that the paste itself has to be designed appropriately to obtain the best rheological characteristics given the blend of the cement fly ash and the brand of the super plasticizer that you are trying to use in the project. Okay. So, you optimize the paste for the best flow, and that obviously involves a combination of your marsh cone and mini slump test, which we discussed earlier. Okay. So, let us look at this stepwise process. First is optimization of the powder combination. Now, of course, we start off with a certain requirement for the SCC. How does SCC get specified? Any idea? How will you specify SCC on the site? It is not enough to just say I want self compactable concrete. There could be some problems if you just say that, because you can produce SCC to have a slump flow of 550 millimeters, you can have SCC that has a slump flow of 750 millimeters. What is the essential difference between the two? So, for example, if I choose different types of structures, let us say I choose a column and then next I say I choose a slab. Okay. I want to design SCC for a column and for a slab. What will be the difference in characteristics of the SCC that I desire? Of course, both have to be self compactable, they need to pass all the tests. But if I have to choose the slump flow of the SCC for the column or for the slab, where do you think I need a greater slump flow? I need a greater slump flow for slab. Why? But then your application is much easier, no? All you have to do is move the chute around and fill up the space. Why do you need to really make it flow a lot? Now, what I am trying to tell you is, if you make the concrete flow too much for a slab, you may get problems. Can you tell me what problems you can expect? Okay, that will happen in any case. The formwork may face a lot of pressure because of self compacting concrete, obviously, because when it is fresh it is highly workable and it will almost exert hydrostatic pressure, right. But then that may happen in all the cases, whether it is a beam or a column or a slab. Why high flow is a problem in the slab? But then you know exactly the amount of concrete you are putting in. So, let us say you have worked that out, not a problem. But after you lay the concrete, what problems can you expect with the slab which you do not have with the column? You have a problem of plastic shrinkage. Yeah. Plastic shrinkage can be very large with the slab, especially if your flowability is high. How is the flowability maintained at a high level? Maybe you have a little bit extra water in it, maybe you have more super plasticizer in it. So, if you have more super plasticizer, what do you expect will happen at the setting time? Setting time will also increase, the concrete will now set much slower. So, the risk of plastic shrinkage goes up as the setting time of concrete keeps on increasing. Okay. The other problem with the slab is that if you have not designed your top cover properly,
if you have not designed top cover, for example, if I have, let us say this is my formwork of the slab and I fill up the concrete into the slab, I have reinforcing bars just lying underneath and my top cover is, let us say, 15 millimeters. Now, I have designed this SCC with a maximum aggregate size of 20 millimeters. So, if you consider the reinforcing bar here and there is an aggregate piece that comes on top, what will happen in this aggregate now? It will start settling around the reinforcement. So, if you have very high flowability of your SCC, you will get what is also known as plastic settlement. And this plastic settlement can lead to some cracks occurring right on top of the reinforcement. Indeed, when people started using SCC, when they produced high flow SCC and started applying it for slab, one of the primary problems that they saw was plastic settlement cracking. You would actually see the layout of the reinforcement on top because the concrete had started settling around the reinforcement. So, you started getting cracks just on top of the reinforcement. Now, we saw this problem in some of the structures that were actually designed within IIT campus. You know, you have seen the engineering design building. The engineering design building had slabs laid with SCC on top, and these slabs we started seeing these problems of plastic settlement cracking. So, what we tried to do was, when we designed the same SCC for the slab that is right outside your library for which holds the chilling water plant for the air conditioning of the library, that slab we took precautions to ensure that we will not get this type of cracking. Okay. Professor Gettu, how many of you know that his house is entirely built with SCC? Okay. He put into practice what he was teaching in class and made all the structural elements including columns, beams and slabs with SCC. And there, those were the early days that we were trying to work with SCC, and he realized that again, when high flowability SCC was used for the slabs, he started getting cracks. So, his house was an experiment that he was conducting to really get some real time data, and it worked out quite nicely. We understood that high flowability in slabs could be a dangerous thing. Now, for a column, how will you pour SCC for a column? Yeah, you probably cannot pour it from the top because it will cause segregation. SCC is highly flowable. So, you will start pouring, or you will input the concrete from the bottom, you pump it in from the bottom and it just goes up, and that is actually an ideal situation because it will completely fill up the formwork without any air gaps. If you pour from the top, one, you have the risk of segregation, the other is that you can create air gaps inside. Okay. So, now in a column, having a high slump flow may be quite useful. Secondly, there is no danger of plastic shrinkage or settlement because it is entirely enclosed, there is no problem there, right. So, the design of self compacting concrete would be specific to the type of situation that you have with the SCC. The characteristics of SCC desired may depend on the kind of structural element, but of course, you also have the requirement of the strength. What do you do then? For the strength, what do you do? How do you design SCC for strength? Again, you assume the same water to cement ratio relationships that you typically get with ordinary concrete, right. Yeah, that is a good starting point. You may not get the same answer, but at least for a start, when you want to design SCC, you consider strength depends on the water cement ratio, and for a particular strength you choose the right water cement ratio and design your SCC based on that. Okay. So, now you have a concrete that is designed for a specific application. It requires to have a certain flowability, and the amount of fly ash substitution of cement needs to be determined for this case. Okay. Now, the issue is you can conduct trials. You say I want to put 10% fly ash, 20%, 30%, 40%, whichever gives me the best flowability will be the amount that I use. Doing this in concrete obviously requires a lot of effort. So, can we narrow this down by working at the paste level, and that is where this test called Puntke test is quite useful, and this is something that Prakash picked up when he did a internship at the University of Karlsruhe in Germany, and they were using this test quite often for optimizing powder suspensions, right. So, here in the Puntke test, the principle is simple. When you mix two different powders, okay, the mixing has to be done in such a way that the combination gives you an optimal packing. That means you have the lowest void content. Okay. So, when you mix two powders, how do you determine void content? You simply mix water into the powders. Okay. At the very early stages, assuming the reactions are very less, okay, this water will just fill up the voids between the powder, and any excess water will come up to the surface. That is all. That is the principle of this test. Of course, instead of water you can use a different fluid also which is not reactive, like kerosene for instance. I will show you the results which will make it clear that irrespective of the fluid that you choose, it seems to give you the correct sort of a picture in terms of the best combination. So, here basic principle is water fills the voids in between the particles. So, the water which remains in excess after filling the voids comes up to the surface, okay, indicating that your mix has reached saturation level. So, that is a very simple test to do. All you need is a beaker, you need a spoon, you need a stopwatch, and you need a water dispenser, a squeeze bottle for the water. So, what do? You have dry mixing first for the homogenization of the cement and fly ash particles, then you add water into this mixture slowly until it acquires a closed structure, and then when you tap the beaker, right, water simply comes up to the surface if saturation point is reached. Okay, after it fills up the entire void, it comes up to the so here this is a photograph which shows you humid cement particles. That means there is water inside, but it is not large enough to come up to the surface. But here the second picture, you have the case of a saturated combination of cement and fly ash, where the water has actually come up to the surface, forming a sheen on the surface. So, you repeat this experiment multiple number of times. It only takes you a few minutes each time to get this done right. Only thing is, you need to quantify the water exactly to ensure that you are able to calculate how much water you are adding to the system. So, based on this, what you do is you plot the packing density versus the amount of one constituent by volume. So, here the constituents are cement and fly ash. So, you can plot the graph either in terms of cement percentage by volume or fly ash percentage by volume. Okay. And what is the packing density? It is nothing but 1 minus void content, and void content is the volume of water divided by total volume of the system. Total volume is volume of the powder plus volume of water. Okay. Volume of powder is equal to volume of cement plus fly ash. So, for each combination you need to determine the volume based on the specific gravities of the materials. Okay. And so, if you plot this, what you see is when you use only water, you get a packing density of around 0.61 to 0.62. This happens at a 60% cement content, that means 40% fly ash content by volume. Okay. If you look at water plus superplasticizer, which is used as a fluid, it again gives you the same 60-40 combination, but it gives you a slightly better packing. It gives you a slightly better packing. Obviously, you expect that because there is better dispersion of the particles, right. And then finally, when you use kerosene, you again get the same 60-40 combination, but you get a still higher packing density. So, what you can see from this is that irrespective of the fluid that you use, the combination that gives you the best packing density is still the 60-40 combination by volume. By mass, it may approximately be about 70-30. So, by volume 60-40 combination of cement and fly ash gives you an optimal packing density. What this means is, now you need to design the paste with a 60-40 combination of cement and fly ash by volume, and that already cuts down one of the variables that you have in your mix design process for SCC. Okay. So, simple test, easily performed, results are obtained very quickly, and you have a fairly good estimate of what combination will give you the best packing. Now, we have packed the cementitious system. How do we pack the aggregate system? So, now if you really look at it, there are methodologies that are proposed by the standards. There is an ASTM standard, ASTM C29, which gives you indications of how best you can pack aggregates. So, even if you are doing a regular mix design, supposing you have 3 different types of aggregate, 20 mm, 12 mm and then sand, okay, you can experimentally simply keep on mixing different combinations of these materials, compact that into a cylindrical bucket and measure the unit weight. The unit weight which is maximum gives you the density which is maximum, right. That means the combination that gave you the maximum unit weight is the optimal combination with respect to density. Okay, the problem there is when you mix this and then try to compact this into a cylinder and do 25 times rodding and all that by the regular techniques, that involves some subjectivity. So, can we make this test a lot more objective was the issue that we were contending with. So, here again you have 3 different types of aggregate, 20 mm, 12 mm and river sand. All you do is first make mixtures of these in different proportions. Let us say we start with 50% sand, 25% coarse aggregate, 20 mm and 25% 10 mm coarse aggregate, 12 mm coarse aggregate. Now, you know very well that when you are designing self-compactable mixtures, the flowability is very high. So, to avoid the dangers of segregation, you will proportion it in such a way that you already have a high enough fine aggregate content. So, you will never choose fine aggregate contents for SCC that are less than 45% of the total aggregate content. If you look at any design for SCC, the fine aggregate will be closer to 50% of the total aggregate content. So, you design your mixtures of the aggregate combinations with 50% fine aggregate and different percentage combinations of 12 mm and 20 mm coarse aggregate, right. And you do the same with 60% fine aggregate and then different proportions of coarse aggregate. Maybe you can also try 40. So, you have a number of different combinations which are possible, okay. And each of these combinations you first prepare a dry mix, intimately mixing these aggregates together. So, what we devised was this bucket method of testing. So, here we have a top bucket similar to your compaction factor, right. If you remember compaction factor test, the freshly made concrete is filled up into the top bucket, the door is opened, it falls into the second bucket, again you open the door, it falls into a cylinder, and the amount of concrete filled in the cylinder as opposed to the amount of concrete that would be filled if you vibrate, that gives you the compaction factor. Here what you simply do is you allow the mixture of aggregates to drop from this bucket into this cylindrical container and measure the density of the aggregates in the container or unit weight of the aggregates in the container. So, instead of just making the same mixture and putting it inside and rodding it to compact it, all you have done is just compaction energy has been given by dropping it from a height, that is all you are doing here, okay. So, that you just measure the unit weight and based on that you can calculate the void content of the system. Void content of the system is nothing but the volume of the container minus the volume of the sand minus the volume of the 20 mm aggregate minus volume of 10 mm aggregate, that divided by the entire volume of the container. That is the voids content that you get in the system, okay. Of course, packing density is nothing but 1 minus void content. Simple enough test once again, but interestingly gives you very good results. So, what you get is, of course, to make this test work, because you have a ternary combination, so you will have to work with multiple number of combinations, okay. So, what Prakash did was he picked up very specific combinations and then he did an interpolation using a mathematical software, okay, which was created in MATLAB. So, where these data points were actually fixed based on the determination which is required by the software, only some of these data points were actually measured and checked, okay. So, based on this interpolation, the contours representing the packing density were worked out and the zone where maximum packing density was obtained was easily identified by this software. Now, actually if you look at it, this software which I talked about in the last class, Europack, which I said was commercially available for a price, and that Europack essentially does the same thing. It does the same thing, it just takes the particle size distributions of the individual aggregates and that does a mathematical interpolation to combine the aggregates and get the suitable packing density that you get when you mix different types of aggregate together. So, here what was seen was the best packing densities were obtained with volume fractions of about 50 to 60% of the river sand, okay, and smaller amounts of 12.5 mm aggregate and slightly greater amounts of 20 mm aggregate, okay. So, how do you read the Ternary diagram? Is the same way as you read the Ternary diagram in the case of your cementitious systems, right. So, here this is 100% 20 mm aggregate and 0% river sand. Here it is 100% river sand and 0% 12.5 or 20 mm aggregate, and this is 100% 12 mm aggregate and 0% of sand and 20 mm aggregate. So, that is how you will read this, just like any other ternary diagram, okay. So, based on this you have arrived at the packing density that is required to give you the best aggregate combination. So, if you are running a ready mix concrete plant for instance, all you need to do is, based on the supply of the aggregates that you get, keep these diagrams ready. So, whenever you need to design an SCC, you can optimize the aggregate combination. This does not need to be only for SCC, it could be done for any other regular concrete case also. When you are doing conventional vibrated concrete, you will not be choosing very high amounts of sand. Your sand contents in regular concrete will be how much? 30 to 40%, not more. Yeah, if you are making pumpable concrete, you want to increase the fine aggregate content. If you are making regular conventionally vibrated concrete on grade, which is not getting pumped, then 30-35% is good enough. So, this ideally suited for RMC plants, but if somebody wants to do this design on their own, if they want to start off doing an SCC design, it may not be suitable, because how will they have access to so many different materials and then try to understand how well these things combine together and so on. So, not a practical solution for individual users. So, something much more easier and simpler needs to be done for individual users. And what is it that can be done? So, here what was done was an analysis of what factors can affect the packing density. One is the particle size distribution obviously. The shape of the particles is also important, because if you have circular or spherical particles as opposed to angular, you get different packing densities. The method of compaction is another important ingredient that can affect the packing density, and the wall effect obviously, depending upon the size of your particles and the shape of the container or size of the container. So, the particle size distribution was considered to be the primary factor affecting packing density, and what we tried to do was model the particle size distribution using a single parameter. You know very well from your PhD studies that there are different parameters designed to describe the shape of your particle size distribution. You have the uniformity coefficient, you have the curvature coefficient, yes. So, it defines the characteristics of your diagram. So, what we thought was, okay, let us try and choose a parameter like uniformity coefficient, because that gives you, since it is a ratio of your D60 to D10, it gives you a range of spread of your particle sizes. So, the greater the range of spread, it is likely that you will get better packing, because more sizes of particles are included. So, greater the range of spread, you get the better packing. So, here what we saw was, when we started using Cu to describe the particle size distribution and saw its effect on packing density, we saw that the packing density was very nicely correlated with the coefficient of uniformity. Okay. Now, what you need to simply do is get the individual particle size distributions, make several trial calculations just based on combined particle distributions, and obtain the Cu values for each, and based on this relationship you can actually get the packing density as a function of the Cu. So, once you get the packing density, the void content is nothing but what? Void content is 1 minus packing density, just 1 minus packing density, right. So, this correlation, we looked at a number of different types of aggregate, it seemed to work quite well for the design of SCC. Using this system of combining the aggregate proportions, we wanted to see whether it really works well in concrete or not. So, to do the concrete design, what we did was, we kept the paste composition and paste volume as constant. Okay, the paste volume was 388 liters per cubic meter, that means the aggregate volume was 612 liters per cubic meter, right. So, the proportions of the aggregates that were giving different packing densities from 0.64 to 0.68 were chosen, and then we tried to look at the effect on slump flow. You can very clearly see here that the slump flow increases as I increase the packing density. Okay, the paste volume is now constant. It is not really a surprise that the slump flow is increasing. Why? Because here look at the packing density, that means the void content here is 0.36, here it is 0.34, here it is 0.32. In other words, in 1 cubic meter you have 320 liters of voids here, 340 liters of voids in this case, and 360 liters of voids in that case. When you add 388 liters of paste, you are filling up the 320 liters of voids, and you have 68 liters extra of paste. So, obviously it will have better flowing ability, you have more paste available now in the system. Okay. So, this paste now enables your concrete to flow better. So, that is why your slump flow increases. Slump flow with J-ring is also a much better performance when you go for the higher packing density. The compressive strength also increases, okay. Although the increase is not substantial, but still there is an increase at least between 0.64 and 0.68, you are increasing your strength by more than 10%. So, you can still call it to be quite significant. So, again what we could clearly demonstrate with this was that the strength as well as the flowability was increasing as a function of the packing density. Okay. You can look at it another way. If you want to keep the workability constant, if you want to keep the flowability constant, you will need lesser amount of paste for the system that has higher packing density, right. You can adjust the paste content so that you get the same flowability. So, you need lesser paste for the case with the higher packing density, and that again leads you to having better savings for your concrete design. So, again we did another test here to see whether the mixture proportions of the aggregates that were giving the same packing density, how was that affecting the properties of the concrete. So, all these mixture proportions were giving the same packing density, okay. Now interestingly, if you look at compressive strength, all these mixture proportions that gives same packing density gave almost identical compressive strengths. You can see that the difference is almost less than 1 megapascal between the concretes. So that strongly again tells you that packing density is very well related to the compressive strength. Okay. In terms of flow, there was a lot of variation. Now why did this variation happen? Primarily because of the effect of the fine aggregate content in this, because you can get the same packing densities with different combinations of the aggregate, but the ones which have the potential to flow most will be the ones which have the greater fine aggregate content. So again here we saw that the ones which had the ideal proportions were actually able to get you much better flowability. Now of course here when you go in excess of 50%, what is happening is too much fine aggregate in the system is also increasing the water demand of your system, and you are not getting the required flowability characteristics. So here you have a situation where even though the same packing density is there, you do not really get the same flowability, but the strength is quite similar. And in some cases of course there was even segregation when the aggregates actually remained in the center and did not flow out with the concrete. So that indicates that the performance is not really very good. That is because you have too much of the 20 mm coarse aggregate, the large sized coarse aggregate. Okay, so what about the effect of the water powder ratio and paste volume? Now you know very well that water to powder ratio, water to binder ratio, as you increase it, you expect the flowability to go up, right. So here what is plotted is a slump flow versus the water to powder ratio by volume, and for different powder contents 350, 450, 550 and 650, these graphs are now created. You see that for 350 powder content you have to go for a very high water powder ratio to obtain self compactability, and there again you have a situation where it could start segregating because the amount of powder is too less. The aggregates do not really have some highly viscous particles supporting them, so aggregates can start settling, but for flowability you still need a high water content in this case. But this means that you can still provide, you can still make SCC with such a low water content because of the design of the aggregate by particle packing approach. Now in terms of the other powder ratios, as you increase the water powder ratio, the slump flow increases, and that is an obviously expected result. You do not expect that to be any different. Now the interesting part here is we were talking about the fact that excess paste is there in the system which makes the concrete flow. So what is the amount of excess paste that is required to achieve self compactability over and above the void volume? So what is plotted here is the slump flow versus the paste volume in liters per cubic meter. Okay. So here you get a fairly linear relationship that describes the slump flow as a function of the paste volume. What does this tell you? As you increase the amount of paste, keeping the aggregates constant, you are expecting a greater and greater increase in the slump flow. So how much extra paste do you want in the system to make the system flowable over and above what is already there, okay, in terms of voids? So that for that what you need to do is look at data that was not only published from this research, but also compare it from data from literature, looking at the mixed designs and trying to figure out what is the total paste content and what slump flow did that lead to. So here slump flow is plotted against the excess paste volume. What do you mean by excess paste volume? It is the volume of paste over and above the void content left behind by the aggregate. So here again you get a very good relationship, and it intercepts the x axis at around 50. That means you need at least 50 liters extra of paste to really have a slump flow which is above 500 millimeters. So usually most self compacting concrete applications you will see slump flow required will be above 500, 550 millimeters. So if you want to get that, you need at least 50 to 70 liters of paste over and above the voids content to achieve that slump flow characteristic. Okay. So what this tells you is you can start off your concrete mixture design for SCC by doing an aggregate combination, determining the voids content, and already your paste content is worked out as something that is at least 50 to 70 millimeters, 70 liters above the voids left behind by the aggregate combination. So good starting point for your SCC design. But the paste itself needs to be again optimized to give you the best performance, and for that we have talked about the fact that you can determine the optimum dosage of superplasticizer using marsh cone, right, and then look at the spread of the cement paste using mini slump. So in this case what was done was the optimum dosage was not only picked out from the marsh cone test, but we also wanted to pick it out as a point that led to about 160 to 180 millimeters spread in the paste. Of course, please remember the paste had 60-40 combination of cement fly ash by volume, okay, and then the water to cement ratio was based on strength. Water to cement ratio was based on strength, okay. So the paste was prepared with different dosage of SP, and the dosage of SP that led to a spread of 160 and to 180 millimeters, which was always to the right of the optimum dosage, okay, was taken as the dosage required to produce SCC. And for that dosage, what we also did was of course, this is again plotting the mini slump spread versus the superplasticizer content by weight, and the 160 to 180 is being achieved at that level of dosage. So what we saw was the optimum dosage obviously was dependent on the water powder ratio. As the water powder ratio increased, the optimum dosage required to get the mini slump spread in the correct range was reducing, and that we expect anyway. As the water increases, you will need less superplasticizer. But that we did not stop at that, we wanted to characterize the rheological properties of this type of a paste, and for that we used the viscometer, which is typically used for measurement of viscosity of asphalt. Okay. So here again you have a outer cylinder, just like we discussed with coaxial cylinder rheometer, and this is a inner cylinder which is made to rotate. The paste basically gets sheared between these two cylinders and registers a torque in the instrument. The torque versus RPM is plotted, and then you get the shear stress versus shear rate relationships. Okay. Now, when you test fluids, what you need to do is, if there has been a previous mixing history, for example, you would have prepared the paste by mixing it in a Hubbard mixer. So, that previous mixing history has to be erased before you do this flow experiment by doing some specific shearing profile. You do a pre-shearing, that means you mix it first for some time, and then you give 30 seconds for it to stabilize, and then you keep on increasing the speed and then decrease the speed, and when you increase or decrease the speed, you start measuring the torque. Okay. So, again we will not get into the specifics of how this measurement is done. Essentially you produce this graph between shear stress and shear rate, and this graph gives you obviously values of yield stress and plastic viscosity like we saw earlier. If you are approximating this to a Bingham model, you can plot the linear relationships and get an estimate of the yield stress and plastic viscosity. As the water powder ratio increases, what happens to your plastic viscosity? It starts decreasing. Okay. Now, interestingly, your shear stress is not really varying much. It is between 0 and 2 pascals. So, it is almost like close to 0. For a self compactable paste, your yield stress should be almost 0. The concrete, again, because it spreads like anything, it has almost a 0 yield stress. Okay. So, yield stress is close to 0. So, what we did was, based on this optimal choice of the paste, we determined the fresh and hardened properties of SCC. So, again this is just giving a snapshot, different water powder ratios, different powder contents, paste content was kept at the same level, the aggregate combination was kept at the same level, and based on this we obtained slump flow between 550 and 650, and as you can rightly estimate, the slump flow increased as you increase the water powder ratio, and that is quite expected. The T500, time taken to spread 500 millimeters, reduced as you increase the water powder ratio. Again, you expect that more water will start spreading much faster, less water will be more viscous.